In this video, we're going to continue our study of the binomial theorem and binomial coefficients, and we'll derive a different identity. This time it's the sum of rho of Pascal triangle identity, or at least that's what I call it. And here's Pascal's triangle, at least partially. It goes on like forever. But what we have is, if you look at the sum of each row, we have this would be 1. The sum of this row would be 2. The sum of this row would be 4. This sum is going to be 8. And this sum is 16. So it looks like they're powers of 2, right? You could say this is 2 to the 0, this is 2 to the 1, 2 to the 2, 2 to the 3, and 2 to the 4. And they're connected by this n. So there's 1, n equals 2, and so forth. Okay, and so in general, the identity is sometimes listed as this. So they'll have the sum k equals 0 to n choose k equals to the n. And so we're going to have to prove, using a combinatorial argument, that these two very different looking mathematical objects are equal to each other. All right, so this is the identity that we want to prove. Okay, so the left-hand side, think of it like this. Again, I'm going to tell a story to kind of ground us first. So let's say you're at a pizza shop, and they have n equals 2 toppings. To keep it simple for now, and then we'll abstract it out. And how can you go about deciding which toppings you want on your pizza? So you could have, let's say, jalapeno and pineapple, just to create some conflict amongst my viewers. We have jalapeno and pineapple. I think they both go well on pizza. I think they actually go well together, but that's a different story. And so we have n equals 2 toppings, and you may think of it like a decision for each topping. So almost like the multiplication principle can help us. And you may think of it like a decision tree. So first topping, you're either going to say yes or you're going to say no. And then the second topping, you're going to say yes or you're going to say no. And same here. So just following along in this tree diagram, if I yes to jalapeno and then yes to pineapple, that means yes, I have jalapeno, and yes, I have pineapple. So that's one possible way to get my pizza. How else can I get my pizza? Well, I could go yes to jalapeno, no to pineapple. And then I'll kind of just leave like a blank X there to say that there's nothing there. All right, you could say no to jalapeno, yes to pineapple. So no jalapeno, but yes to pineapple. And then we have a final one, no to either. You just want like plain cheese. So I'll say no and no. And those are the 4 possible pizzas. So with 2 toppings, there are 4 possible pizzas. Okay, so that seems plausible. So I would say 2 squared pizzas. And in general, like if you had, let's say n equals n toppings. So let's say n toppings now. If you did it the decision tree way, You'd branch these out. I'm running out of room now. But by the end of it, you would have 2 to the n branches. Where each one of these like branches, kind of like here, 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 and here, those represented one of the possible pizzas you could get. And so these 2 to the n branches represent the 2 to the n pizzas you could order. Okay. And another way to think about it is like just, I know some books and people explain it using like some sort of placeholder decision tree. So your first topping choice or decision, you have 2. The second choice, you have 2 again, because you can either say yes or no. So that's why there's 2 choices for each topping. You either say yes or no to each topping. And that is 2 to the n. So lots of ways to think about it, and the more comfortable you are with these representations, the better. All right, so that's one way of counting it. What's another way of counting it though? So again, let's say we have n toppings. Another way your brain may think of it is, well, what if I wanted 0 toppings? How many ways are there to do that? Well, there's one. That's where you just get cheese pizza, right? No topping. Okay. And then you may start to like, you're pretty much partitioning all of the pizzas by the number of toppings they have. So if there's n toppings, then you could also have 1 topping. How many ways are there to do that? Well, there's n ways. And that's because if there's n toppings, like let's say there's jalapeno, pineapple, I don't know, bell pepper, I don't know, garlic, so forth. So let's say there was like 4 toppings right now. Then you could have, if you just wanted 1 topping, you could have jalapeno, or you could have pineapple, or you could have basil, or you could have garlic. And in general, if there is n toppings, there'd be n ways. Okay? And now, again, we're just going to go all the way up to the number of toppings. So, do a couple more. You can order a pizza with not 0 toppings or 1 toppings, but you can order a pizza with 2 toppings. And you could say, all right, well, how many ways are there to do that? And this is when our binomial coefficients start to help us out. Remember, you have n toppings, so your n choose 2. That's the number that you have. So there's n choose 2 ways choosing a 2 combination. Topping pizza, right? Because when you choose the 2 toppings, it doesn't matter the order they go in. So again, example for if there was 4 toppings, there'd be 6 ways. And we've done that one many times. Like you could have jalapeno and pizza, jalapeno basil, jalapeno garlic, pizza basil, pizza garlic, and then basil garlic. So 6 ways. 1, 2, 3, 4. Sorry. 1, 2, 3, 4, 5, 6. And in general, there's n choose 2 ways. And you can continue on, right? So there's 1 way, you go 0 toppings. There's 1 topping, you can do it in n ways. 2 toppings, you can do in n choose 2 ways. And continue on in this fashion. We can say that there are let's say I want to use every topping except one. So I could say n minus 1 toppings. There are n choose n minus 1 ways. And in fact, that would actually be n as well, because you can, if you choose n minus 1 toppings to be on the pizza, you're really choosing the one to be off it, and there's n ways to choose one topping to be off it. So this is actually equal to n as well. And that's from the last video. We actually proved that. We said that n choose 1 is really the same as n choose n minus 1. But that's besides the point. And then finally, you can order a pizza with n toppings. All right, and that's going to be n choose n, and that equals 1 way. All right, and so you basically took, the set of all pizzas. You said, okay, well, I want the ones with 0 toppings, 1 topping, 2 topping, 3, n minus 1, and n. The number of pizzas with 0 toppings is 1. This was n. This is n choose 2. This would be n choose 3. N choose n minus 1. And this would be n choose n. And since these are all disjoint, you can really say the number of pizzas would be 1 plus, or sorry, I won't do 1, I'll just do, really 1 right here is n choose 0. So this is n choose 0 plus n choose 1 plus n choose 2 plus n choose n. And so that's a different way of counting the pizzas. And that is equal to, just by putting in summation notation, k equals 0 to n choose k. So what did we just show? We just showed that there are 2 ways of counting all the pizzas. There is partitioning it and saying this way, where I count 0, 1, 2, 3, 4, n toppings. And that is this summation right here. On the other hand, if we did it a decision tree way, saying, okay, for each topping, you have to decide yes or no. And that led to this expression here. But in the end, it's counting the number of pizzas that are possible. And so those 2 quantities are equal, 2 to the n and this sum here. So I'll just write it out. Therefore, k equals 0 and n choose k equals 2 to the n. Both sides count number of possible pizzas. They just count them in different ways. All right, and that is the sum of a Pascal triangle row identity. And I'll see you in the next video for the last identity, which is actually called Pascal's identity.